Hello everybody, how are you? Welcome to the State Math Counts Competition live stream. This is actually going to be quite hard for me, I think. Just to give an idea of what we're going to do today, we're doing an official collaboration with MathCounts, and it's a huge pleasure to do this because MathCounts is something that got me really interested in math back when I was in middle school. Now, this is the state competition. And the state competition means that it's usually taken by the people who are the best in the state in the middle school math competition. That means it's hard. Now, something about the way we structure this. First of all, since it's an official collaboration, all of the problems are copyrighted. Please do not copy them outside. We are able to do this only because we are officially working with MathCounts. But secondly, they're actually going to be hard, and I have not done them before. The way that I always do these live solves is that I try to show you how I would go about thinking about a problem if I'm looking at it for the first time. And as they get harder and harder, I'm going to need more and more help. We'll see. Thankfully, we have some really good people who are watching this live stream, so I hope that if you have any good ideas, you might also contribute some of them. All right. Well, let's go and switch and start talking about some of the questions. We're going to do this live stream over the course of 3 sessions, although we might discover towards the end that we need more than 3 sessions. Well, we'll find out. Now, the way I do this is because we don't exactly know how many sessions it's going to take, I'm also going to run this in a way where I go a little bit faster than usual. Now, some of you know that when I run these Ask Math Anything live streams on this regular channel, I try to explain things out as clearly as possible. But here, because we're doing some really hard problems and we have limited time, I'm going to assume that the people who are watching maybe are a bit more experienced. And so we're going to be talking through these quite a bit faster. All right, let's go ahead and see what the questions are. Okay, question 1. Let me click this so that I can see it clearer. Question 1. Holly is selling candy bars to raise money for her softball team. She starts with 80 candy bars and sells 32 to her neighbors and 15 to her grandparents. How many candy bars does Holly have left to sell? So it's 80 minus 32 minus 15. That's what I see. So if I want to do 80 minus 32 minus 15, what's the easiest way to do this? Oops, just a second. Let me just hit enter there. So yeah, so what's the easiest way? What's the easiest way to do this? Well, I think it's easier for me just to lump these two together first because that's the amount that I'm subtracting, and then let's subtract it all at once. So this 32 and 15, that's going to give me, it's a minus sign still, but it was a minus and a minus, so it becomes 47. So what I have is subtracting and subtracting more is like subtracting the sum of those. So 80 minus 47 is what I have, and 80 minus 47, that happens to be 33. And here it's like always be careful of the borrowing. 80 minus 40 something is not 40 something. It's 30 something if it's 40 something plus. Reading the question again just to double check that it makes sense. 80, sell those, take them away. 47, quick double check. Yeah, 33. I think it's okay. Let's see if this is correct. Hopefully my arithmetic is correct. It is! Question 2. They're going to get hard. A recipe for chocolate chip cookies calls for 2 1/4 cups of chocolate chips. Jamie only has a 1/4 cup measuring cup. To measure the exact amount of chocolate chips needed for the recipe, how many times does Jamie need to fill up the measuring cup? Okay, so I think it's saying how many 1/4s are there in 2 1/4. Right? Okay, well, 2 1/4 I can rewrite as a common fraction, it's called in MathCounts, but it's just an improper fraction in this case. It's 9 over 4 because 2 is 8 over 4. So in that case, 9 over 4, how many 1/4s are there? There are 9 of them. So I think the answer is 9. It's because I have to know how many times I use the 1/4 cup if I need 9 of them. Let's see if this is right. Yes, let's keep going. If 0.0036 divided by n is equal to lots of stuff, 0.00012, what is the value of n? Okay, well, if I wanted to think of this, it's 0.0036 divided by n is equal to 0.1234 zeros and the 1, 2. So that means n is equal to 0.0036 over 0.00012. I don't like fractions, and I'd like them even less when there are decimals in the fractions. So let's multiply the top and the bottom by a big power of 10. 1, 2, 3, 4, 5, 6. 10 to the power 6 to be specific. If I do that, 1, 2, 3, 4, 5, 6, then I have 0 and 0 here. Okay, so I multiplied both the numerator and denominator by 10 to the power 6, and so the answer is 3600 divided by 12. This is not bad. That's equal to n. So that's 300, because 12 times 3 is 36, so that's just 300. Hopefully this arithmetic is correct. Let's find out. We're good. Question 4. Alonzo draws a diagonal of a convex polygon with 8 sides. The diagonal divides the polygon into 2 smaller polygons, one with 6 sides and one with n sides. What is the value of n? Okay, convex polygon with 8 sides. Stop! It's a stop sign. Maybe it could be a bent stop sign, but it's just a stop sign of some form. Now it needs to divide into 2 smaller polygons, one with 6 sides, one with n sides. Oh, there's a neat thing here. Kind of like, no matter how you do it, like suppose you divided it. Here's what happens. You know what's the sum of the number of sides of the 2 polygons? The sum of the 2 polygons' numbers of sides, well, this is 4, and this is 1, 2, 3, 4, 5. Oh, oops, I guessed it right. I didn't mean to guess it right. I was trying to show you that there's a neat pattern, which is like if you do a diagonal, the sum of the number of sides of each thing is not 8. Because if I look at how many blue segments there are, there's 8 of them for going all the way around, plus 2 more, because there's 2, 1 on each side of the diagonal. So that means that the sum of the numbers of sides of each of the polygons adds up to 8 plus 2. So now I know that the sum of the number of sides, that's equal to the original octagon plus 2 more. I'm doing it this way so it's general. So even if you had the problem and it wasn't an octagon, you could still do it. Okay? But this 8 plus 2 is 10. But there's 2 sides. You know, one of them is 6 sides, and one of them is n sides, is 10. Okay, so n is equal to 4. And I accidentally drew it here. I did not mean to solve it just by accident, but we did. 4. Let's keep going. I just know they'll get hard. Oh, that was the answer to question number 4. It was 4. Those math counts writers have a sense of humor. Oh, interesting. Something happened about our word wrap here. My guess is that this is 4 to the power x minus 5. I'm just going to put a 5 here. Okay, that's probably a 5. And let's just like block this out somehow. Okay, great. So when x equals 3, what is the value of the expression 4 to the power x minus 5, expressed as a common fraction? So 4 to the power 3 minus 5, that's equal to 4 to the power negative 2. Negative exponents are the reciprocal of positive exponents. Again, this is math count state, so I'm not going to explain everything super carefully. And we get 1 over 16. I think that's good. Let's see if that works. Yes, it does. Let's keep going because we know they'll get hard. Sylvia the snail crawls 23 inches in the first hour, then 59 inches in the second hour, then 49 inches in the third hour. How many feet does Sylvia crawl in these 3 hours? Express your answer to the nearest whole number. Let's add up some inches. Oh, wow. Okay. How many feet nearest whole number? Forget about adding the inches. What is this in feet? What's 23 inches? 23 inches is like 2 feet minus 1 inch. What's 59 inches? That's 5 feet. That would be 60 inches is 5 feet minus 1 inch. And 49 inches, that's 48 inches, which is 4 feet plus 1 inch. Look, if I care about the answer where it's like rounding to the nearest whole number of feet, look, these inches, they're not going to do much. There's going to be a net of minus 1 inch. So let's just add these numbers. 2 plus 5 is 7, 7 plus 4 is 11. I actually could just go and even tell you what it was. It's 11 feet minus 1 inch. But so the answer is 11. Okay? And this thing is something where I don't have to actually go and do all of the arithmetic adding up all the small numbers. I hope. Let's see if it's right. It is. Question 7. Ben, Rachel, and Terry collected seashells on a beach. Ben collected 5 more than twice as many seashells as Terry collected. Rachel collected 7 less than 4 times as many seashells as Terry collected. If Ben and Rachel collected the same number of seashells, how many seashells did Terry collect? Let's write some equations because there's too much going on. So I have B, R, and T. And B is Ben. Ben collected 5 more than twice as many as Terry. Okay, that's that equation. Rachel collected 7 less than 4 times as many as Terry. I'll write 4 Terry minus 7. And I also know that Ben and Rachel are the same. Oh, that's nice. Okay, now I can solve this. Okay, Ben and Rachel are the same. I care about T. The thing I always look at is, what am I trying to figure out? Oh, I want T. So let's get rid of everything else. But I can, because B equals R. So let's draw like an equal sign like this. I promise you this is an equal sign. All right, so B and R are the same. So that I've got this big equation. 5 plus 2T is equal to 4T minus 7. And I care about T. So that means 2T is equal to, that looks like a 7. Let me write it more clearly. 2T is equal to 5 plus 7 is 12. Looks like Terry got 6. Okay? And if I was doing this thing more carefully, I might also try to like figure out B, figure out R, plug it all in, see if the question makes sense. But since we are doing a fast live stream, I'm just going to go and say, I think the answer is 6. 6. Next, question 8. At Kickin Chicken, a chicken sandwich costs $4 plus 7% sales tax. If Quincy orders a chicken sandwich and pays with a $20 bill, how much change will he receive? Okay, actually 7% sales tax, I think that's what it is in Pennsylvania, Allegheny County, Pittsburgh, Pennsylvania, where I live. So that's what would happen if I went to Kickin Chicken. Okay, $4 plus 7% sales tax. The easiest way to do these kinds of things is to say that the total with tax is equal to the $4 times 1.07. Adding 7% is just adding 7% means multiplying by 1 for yourself plus 0.07. That's the 7%. And so that is equal to 4.28. Very nice. Not really any carrying because 4 times 7 is 28. And I now just subtract it. So I need to know what is $20. Whoops. I need to know what is $20 minus 4.28. Always the carrying, you have to be careful. 15.72. I should tell you the way I do this kind of subtraction. It's like, I know I'm going to do a lot of borrowing, so I do 20 minus 4, that would be 16, but I'm doing borrowing, so it becomes 15. And then I'll do a 10 minus 2, that's an 8, but I'm going to do borrowing, so it becomes a 7. And finally, the 10 minus 8 is the 2. So that's how I come up to this. But that's, like, after doing enough of these types of problems, you get kind of used to solving these things in your head. Let's see if that's correct. 15.72, Kickin Chicken, coming up. Question 9. In right triangle ABC, point D is on side BC, as shown. If BC is 5 times BD, and the area of ABD, this little guy, is 8 square inches, what's the area of ABC? Oh, okay. So what I'm doing here is, area of a triangle is half base times height. Aha, they have the same base. So I'm going from this little guy, ABD, to the entire thing. So the base is the same. What happens to the heights? Well, DB goes to 5 times dB to get to BC. So the height goes by 5, multiplies by 5. So the answer is that the area just goes from 8 inches, 8 square inches, to 8 times 5 square inches, which is 40. It's 40 square inches for the entire triangle. That seems okay. Question 9, answer is 40. And we're good. Question 10. By selling handmade dolls, Hannah hopes to earn at least $1,500 to donate to the local hospital. That's very nice of her. If she makes between $40 and $90 for each doll she sells, what is the absolute difference between the minimum and maximum number of dolls she must sell to meet her minimum fundraising goal? All right, so I just need to go and compare these two different possibilities. The minimum number of dolls, that would be if you use the expensive kind, 1,500 divided by 90. Oh, it's not going to divide perfectly, but that's okay. Take out take out the 0, dividing by 10. Next, I'm going to divide out a 3, so that's a 3, and that's a 50. Now I need to know what is 50 divided by 3. That's actually going to be a mixed number. Actually, I can tell you, I know 51 is a multiple of 3. 51 is 17 times 3. I'm going to write 17 minus, okay? Well, what just happened here? So what I said is if I take this division, I have 50 over 3. 3 times 17 is 51. And this is 50, not 51. So it's actually 16.666666. But the important thing is I need to round up, right? She needs to actually earn at least $1,500. So when you round up the thing, you will get 17. So the minimum is actually just the 17. I'm going to write round up here. So that's the minimum rounded up. Now, the other thing is I need to know what is the maximum. Well, if I had to do a lot of selling, I'll do 1500 divided by the less expensive kind, 40. So let's do this again. Divide out the 10. Let's use a different color. Divide out the 10. Now I have to do the 40. It's not a multiple of 4. Divide by 2, and I get 75. 75 over 2, that's 37.5. I have to round up, and that'll give me 38. Okay? And now I need to know what's the absolute difference. So I subtract. I say 38 minus 17, and that would be the answer. Thankfully, I don't actually need to do any borrowing. That's 21. And so I think that the answer to this question is 21. Let's see. It's 21. Question 11. A fence is to be placed along the perimeter of a rectangular field with area 400 square feet and minimum possible perimeter. Those are usually when you go and make a square. If 1 foot of fencing costs $2.50, what is the total cost of the fencing needed to completely enclose the field? Alright, so I need minimum possible perimeter. By the way, in America, if you say something is rectangular, it could also be square. That still counts as rectangular. And so I have 400 square feet area. That means it's 20 by 20. It's a square. And so now I need to know, what about this number of feet? That means it's 20 times 4. The perimeter is 80 feet. And I'm supposed to also multiply by the cost of 1 foot of fencing, which is $2.50. So then the answer is equal to 80 times $2.50. Okay. Now I don't need the 2.50, it's just 2.5. What's the easiest way to deal with this? I like 10. Let's take a factor of 4, yank it off of the 80, and throw it onto the 25, or onto the 2.5. Divide 80 by 4, that gives you 20. Multiply 2.5 by 4, it's 10. That's wonderful. So I get 200. So it looks like the fencing is going to cost $200. Let's see. So far, so good. Question 12. If each side of a square is decreased in length by 2 centimeters, its area is decreased by 160 square centimeters. What is the original side length of the square? Okay, cute. So what I've got here is I have an original square. I don't know the original side length, so let's call it x. And each side of the square is decreased. Oops, let's use a different color. It's decreased down to x minus 2. And now it tells me something about the area. So I just need to know if I happen to have that x squared minus x minus 2 whole things squared happens to be 160, what could I say is x? That's all I need to know. So let's start expanding this out. Oh, haha. Now since this is MathCounts state, let me give you a trick. This is a difference of squares, alright? So a difference of squares, something squared minus something else squared, it factors. It factors into their sum, which is 2x minus 2 times their difference, which is just 2. This is the fastest way to solve this problem, I think. So again, what I just did is a squared minus b squared is a plus b times a minus b. Now this is nice, because I see that there's a 2 here and there's a 2 here. Let's divide both sides by 4. Now I get x minus 1 is equal to 40. So x is equal to 41. Okay, and I think that happens to be the answer. Oh, there's something satisfying about this too. I just have to say, I have to geek out over this. Because if we're claiming something about the difference between 41 squared and 39 squared. Yeah, so there's something neat. The difference between squares, you can actually break it up into two of them. 41 squared minus 40 squared. This is how I'm checking my answer. Plus 40 squared minus 39 squared. And there's something that also follows from the difference of squares formula, but it's something that I remember, that I see a lot. I noticed this whenever I played with math problems when I was younger. Plus 40 plus 39. It's like if I had a square going to the next square, then what I add is like the number plus the next number. I just noticed that. And look at that, that's like 4 40s, and 4 40s is 160, it works. And yeah, somebody made a point like, nice trick, not really a trick, it's an identity. I mean, but the idea of using the identity, that counts as a trick. All right. Yeah, I agree. You could have done this by like expanding the whole thing out, but if you watched my live streams, you know that I'm too lazy to do that. Is the answer 41? We are good. Let's keep going. In Mr. Patterson's class, the average score among students who studied for an exam was 78. The average among students who did not study was 54. So make sure you study. The overall class average was 70. What portion of the class did not study? Express your answer as a common fraction. Ooh, okay. So this is cool. So I always think of this as like some kind of a balance scale, okay? So 70, 78, it probably looks sort of like this. This is the balance scale. This is 70, this is 78, and this is 54. Okay. Now, the nicest way to do this is to say, how much is 78 above 70? That's plus 8. How much is 54 below 70? That's 16. Aha. So what's really going on here is you really do have a balance, right? The point is, if you had equal numbers of people with each score, then the average would be smack in the middle. But you don't. You have more people with a particular score. So the fact that the average moved all the way over to here, that's sort of like how if you had this seesaw and you just had like more people sitting on this side of the seesaw, then you got to move the thing over to balance. And again, in a longer live stream or in our algebra class, we could explain this thing out properly. But here, effectively, all that's going on is we're saying, this 70, 78, and 54, the numbers themselves don't matter. It's the amount they are different from the average that matters. And since I have twice as far this way, I need to have twice as many people here. So the ratio of how many people are on each part is there is one person here for every 2 people there. And that means the fraction of the class that did not study is 1 over 3. Okay? And this is the fastest way to do these kinds of problems. And effectively what we've just talked about is this is the notion of a weighted average. If I have different fractions of people who have different values, then I have to go and multiply by that weight. But this physical idea also actually helps too. Okay, is it 1/3? Let's go and find out. Yes, it is. Let's keep going. Oh, that was cute, by the way. That was question 13, and the answer was 1/3. Question 14. 40 balls numbered 1 to 40 are placed in a bag. What is the probability that the number on a randomly drawn ball is a multiple of 4 or 5? Express your answer as a common fraction. Oh, okay. This is a number theory problem. Now, one nice thing is that the LCM of 4 and 5 is 20. In particular, both 4 and 5 are factors of 40. Now that actually tells me that I can use something called the Chinese remainder theorem. There's a very nice thing where, since 4 and 5 are relatively prime also, let's put that down also, these two are relatively prime too. Since I have these two numbers which happen to be relatively prime, I actually can use what's called the Chinese remainder theorem to go and say the probability of a number being divisible by 4 and being divisible by 5 is actually independent. This is a very strong statement. So what's going on here is, because of these statements I've just made, it's so the probability of a number in 1, 2, up until 40 being a multiple of 4 is independent of the probability it's a multiple of 5. Okay, that's actually going to let me do some multiplication. Now, of course, if you're not comfortable with this way, if you actually went and drew out I guess the first 20 numbers, you'd notice a really neat pattern that somehow... Should we just do it? Maybe we should just do it, since we seem to be doing quite well on time. Okay, we're doing quite well on time, so I actually want to show you some neat math. So first of all, I want to solve it quickly, and then I want to explain why that's so cool. So first of all, once I have this independent property, it's going to be awesome, because I just need to know the probability is a multiple of 4 or 5. Okay, so what I'm actually going to do is let's first find the probability that it's not multiple of 4 and not multiple of 5. It's the opposite, the complement. So not multiple of 4 and not multiple of 5. Perfect. Not multiple of 4, that's 3/4. Not multiple of 5, that's 4/5. So that's 3/5. So the answer is 1 minus that. So the answer is equal to 1 minus 3/5, which is 2/5. Before I start showing you why this amazing thing works, let's make sure it is actually amazing. What's the answer? Yes, it is amazing. Now let me show you why it works. Okay, so now what I just said about this independent notion is it's a little bit crazy. It's like, let's go and look at what the numbers are from 1 to 20. Just realized my fridge is making a noise. Let me close this door. You guys don't need to hear a tick, 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 tick sound. Okay, so now what's the deal with like the first numbers from 1 to 20? I'm actually going to draw them from 0 to 19 because things repeat. So what I'm going to say is let's just draw some numbers first. Some numbers: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. So now what's going on is that some of these are multiples of 5. These are the multiples of 5. And the important thing is like the multiples of 4 are what is called independent of it. Let me circle the multiples of 4. One of them there, one of them there, one of them there, one of them there, and one of them there. Oh, neat. I can actually even think of them all as like on that thing plus that. Okay? But when I said independent, the important thing is like if a number happens to be a multiple of 5, first of all, you can already see the fraction of things that are green circled is 1/5. So the probability that a number is a multiple of 5 is 1/5. The probability it's not is 4/5. And the probability that a number is a multiple of 4 is 1/4. There are 5 things circled, and the chance of it not being a multiple of 4 is 3/4, all the rest. But the independent tells me about how the two things intersect with each other. And so among the multiples of 5, notice that exactly 1/4 of them are multiples of 4. The notion of independence is if I knew it was a multiple of 5 and now I focus there, what's the chance that I'm a multiple of 4? Oh, it's the same as if I didn't focus there. So that I get some independence. That's what's going on here. And actually, if you look at the rest, the chance of it being, if I was not a multiple of 5, the chance that I'm a multiple of 4 among there is still 1/4, because somehow not being a multiple of 5 is over here, and exactly one thing in each column got picked. So 1 out of each 4 in each column. So it's just really nice. There's this independence going on. And this happens precisely because I was doing with the numbers from 1 to 40. You might wonder why I put a 0. It's because 1 to 40 and 0 to 39 would give me the same answer. Because the 40 and the 0 have the same divisibility properties with 4 and 5. And so I basically have 2 batches of this picture. Okay, so that's what's going on here. This is a fairly sophisticated problem where if you think about it with this Chinese remainder theorem, it ends up falling apart. If you do it slowly, you can also do it slowly. All right. Somebody just asked me, are there real people, students in front of me? Well, all of you. I mean, I don't actually have anyone else in this whole room where I am. I'm just in the middle of I'm in my teaching studio. This is where I do all my live streams. But the people who are real in front of me, all of you. Okay, let's keep going. I think that there's something here we need to adjust on the layout. If 3 to the power 3 to the power n, I think it looks like that. If that's supposed to be 27 to the 27 to the 27, what is the value of n? Well, that's a cute question. Let's find out. Well, first of all, I need to make this thing look like 3 to the power something. So let's replace out the 27. The 27 is 3 cubed. Oh, let's do it this way. The 27 is 3 cubed, now raised to the power 27 to the 27. Okay? Now, that's important. I have a number raised to the 27 to the 27 power. Wait. No! Wait, oh, maybe it's okay, maybe it's okay. We'll see. This seems like it could be very large, but we'll find out soon. Okay, great. Oh, it's not that large. It's okay. So it's going to be 3 to the something. I need to know what that something is. I need a power of 3 to express that something. By the way, that something is 3 to the power 3 times 27 to the 27. Aha! That means the 3 to the n is that thing. So now I want to know 3 to the n is equal to 3 times 27 to the 27. Let's just do it again. 27 is equal to 3 cubed. which is 3 to the power 1 times 3 to the power 3 times 27. I know that. That's the next power of 4, 81. So it's 82. It looks like I have 3 to the 82 is 3 to the n. So n is equal to 82. At first I was really scared because I thought, oh no, is it going to be just like huge? Because I see all these 27s. I don't like to take like big messy calculations. But fortunately, hopefully the answer is right. It's 82 and it's right. Let's keep going. Question 6. Question 16. It says, Paloma has a bag containing red, blue, and white marbles. The ratio of red to blue marbles is 4 to 3, and the ratio of blue to white marbles is 7 to 2. What is the probability of Paloma randomly drawing a blue marble from this bag? Express your answer as a common fraction. I see I'll have to do something to bring them to the same form, like the same common factor. So I have red to blue to white. I have red to blue is 4 to 3, and I have blue to white is also 7 to 2. Here's how I'm going to do it. I want them both to have the same number here. So I'll put a 21. Now let's scale this. If I scale the red to blue, that's just timesing by 7. 3 times 7 is 21. 4 times 7 is 28. And by the way, I can now put the whole ratio across, because if I want to go from 7 to 2 to 21 to something, you multiply by 3. Okay, so now I actually know the red to blue to white ratio. It's 28 to 21 to 6. And that's actually why it's convenient to write ratios with colons, because we can write ratios of like 3 things and say it's this to this to this. Whereas if you just write ratios as fractions, you can't do that. Okay, well in that case the question was, what is the probability of Paloma randomly drawing a blue marble from the bag? So I want 21 divided by the sum of everything. What's the sum of everything? That involves arithmetic. Oh no, I'm bad at that. 28 plus 21 plus 6. Okay, 8 plus 1 is 9, 9 plus 6 is 15, that's 55, and so the answer is 21 over 55. I have to check, do I need to simplify that? Well, 21 has a multiple of 3, and is a multiple of 3, is a multiple of 7, 55 is only 5 and 11. I think we are good. This is the chance of a blue marble. 21 over 55. Let's see. It is. Still got some time. We're about halfway through, and we're on like halfway through the sprint round. Riley's entire extended family goes out to eat. Each person orders either a salad for $6.50 or a cheeseburger for $7.50. They spend a total of $138 and buy 4 more salads than cheeseburgers. How many people, including Riley, are in the family? Okay, so there's a whole ton of people here. Everyone is either getting a $6.50 or a $7.50. Okay, and there's going to be 4 more salads than cheeseburgers. Oh, here's how I'm going to do it. So in that case, let's transform everything into cheeseburgers. Would that do it? No. That's not going to do it. 4 more salads than cheeseburgers. Ah, see, I'm trying to like cheat a little bit. All right. So I'm going to be like, no. Here's what I want to do. The chef, or not the chef, the waiter. The waiter is going to mess around with them. The waiter is going to be like, do some switcheroo and say, yeah, let's go and switch 2 of your salads for cheeseburgers. Now you have the same number of salads and cheeseburgers. I know you can do this with algebra, okay, but I'm lazy. So what I'm going to do is I'm going to do a switcheroo. Oops. What we do is we go and say, let's go and like change 2 salads into cheeseburgers. Change 2 salads into 2 cheeseburgers. You know, like maybe the waiter just heard the order wrong. And because they heard it wrong, it's suddenly same number of salads and cheeseburgers are showing up. So now you get the same number of salads and cheeseburgers. I'm just going to write burgers. But the cost changed too, right? I'm saying that the waiter taking the order misheard. So it's not like they're giving you the wrong food. It's like the waiter just misheard. I thought you wanted to have equal number of salads and cheeseburgers, okay? Well, if that happens, you know what? With this swap, how much more expensive is each cheeseburger? Each cheeseburger is an extra $1 over the salad. So the same number of salads and cheeseburgers, and the total cost is $2 more, $140. You see why this is nice? Okay, so what I just did here is I said they were supposed to spend 138, but just kidding, the waiter messed around with it and said that you get 2 more cheeseburgers. That is going to then cost you $2 more. 138 becomes 140. You know why this is nice? Now, suddenly it's like, imagine you have a bunch of pears. How much is a salad and a burger together? Forget about these 50-cent things. Those are annoying. If I take 2 of them together, one salad cheeseburger combo could be called a combo meal. A combo meal is $14. Each salad plus burger combo is equal to $14. So how many combos do I have? 10. I've got 10 combos. 140 divided by 14 equals 10 combos. But the question wasn't how many combos there were, it's how many people there were, including Riley. And Riley is one of these people counted here. So like, don't forget to double it. The combo is 2 things. And that is 10 times 2 equals 20 people. Whoops. I want to put a box around the 20. Okay, let's see if this actually works. It is. It's right. So I want to revisit what we just did here. You could totally have done this with algebra and equations, but I sometimes just like to look at something and say, can I be creative enough to make it so I don't have to write down any of these equations? And in this particular case, the answer is yes. All you have to do is you just like say, this is really annoying, 4 more salads than cheeseburgers. Let's go and mess around with it, fix it. And now they're equal. And poof, it's done. Okay, next question. Number 18. ABCD is a rhombus with side length 6. The measure of angle ABC is 150 degrees. Segment BE is perpendicular to base AD, and F is the midpoint of segment BE. Looks all right so far. The length of segment CF, expressed as a common fraction in simplest radical form, is ABC. I think there's a typo here. I'm going to guess it's A root B over C. That's what MathCounts usually does. So I'm going to make a guess that MathCounts wanted this. Okay, and let's go and see what we got. So importantly, I have this 150 degrees, okay, and this is a rhombus. Okay, if it's a rhombus, that's also 150. Let's start to go and look at some of the angles that we happen to know. Or do I even need that? Yeah, I see how to do this. So I kind of want to know what is this piece, and then I can use the Pythagorean theorem to do this, because the side length is 6. So this part is 6. Okay, that's important. That's 6. I'm going to use the Pythagorean theorem. I wish I knew this little bit. It's the midpoint. So if only I knew that bit. But I know some angles. 150 degrees is ABC. 90 is here, so that's a 60-degree angle, even though it doesn't look like one. And this is a rhombus, so this is also 6. Oops, let's use greens for the actual lengths, okay? So it's a 30, 60, 90 right triangle. That means that if this is 6, this is half of 6, even though it doesn't look right. This is the big angle in the 30, 60, 90. 6, this is half of 6, so that whole thing is 3. And this part, which is over here, is half of 3, 3 over 2. And now it's Pythagorean theorem time. Except that I'm also kind of lazy. I would rather do this in a way where there are no fractions and as small ratios as possible, as small numbers as possible. So this particular piece, I can think of it as, in order to get to there, let's do something times 3 over 2. And that something is the 1 against, what should be the other one? 2/3 of 6 is 4. Okay? So what I just did here is I said, you see this? If I wanted to make this 3 halves and 6 into something, well, to turn 3 halves into 1, you multiply by 2/3. To turn 6 into something, you multiply by 2/3, that's 4. And that's why if I multiply by 3 halves the other way, then it works. And I can see 4 times 3 halves is 6. Now this one I can do, Pythagorean theorem. This is the square root of a squared plus b squared, that's square root of 17. So now I just need to know the answer. Oh, that's the answer. It's 3 root 17 over 2. Because I take this root 17 multiplied by 3 over 2. So the answer here is 3 root 17 over 2. And now I need to add 3 plus 17 plus 2. 3 plus 17 is 20. I get 22. Hopefully that's actually what the question meant. So the question here, by the way, it wasn't quite transcribed properly but on our side. But I think the answer is 22. Let's see. It is. We're good. And the thing about this rhombus is it looked a little bit funny, right? And that's because it wasn't drawn to scale. But once you label enough stuff on it, you can see you're just kind of trying to go towards this value. And so you know you got to Pythagorean theorem it somehow. All right, we got some more time. Next question. And they're going to get harder as we get into the last 10. So I need to save up our energy. Question 19. When 257 is divided by m, the remainder is 5. How many possible positive integer values are there for m? Oh, that's interesting. So what this is saying is that 257 is equal to m times integer plus 5. Well, if that's true, let's subtract 5 from both sides. 252 is equal to m times an integer. And that's it. What I mean by that's it is the number of possible integer values for m, possible positive integer values for m, is exactly how many ways can I find a positive integer factor of 252. That's it. And I'm just checking here to be like, does 1 count? Yeah, 1 counts. I mean, whoa, no, this is tricky. This is tricky because 1 doesn't count. If I divide by 1, the remainder is not 5, it's 0. Ooh, a trick question. I almost got caught. Okay, so what's going on here is that, yes, this is true, but you better have that m is bigger than 5. Because if m is less than 5, you're never going to get 5 as your remainder. But you need m to be bigger than 5, okay? So I now need to actually go and factorize this 252 and see like what are the factors, and I want to know how many factors are bigger than 5. So first of all, 252, how do you factor this thing? 252. Oh, I see. It's 2 plus 5 plus 2 is 9. That means I can yank out a whole 9. So 9 times 2 is 18. 9 times 8, no it doesn't. Is it? 9 times 8 is 72. Yeah, 9 times 8 is 72. So yeah, 9 times 2 was 18, 72, 9, 8, 72, okay. And this is like 4 times 7. Okay, so now what I just found out is that 252 is equal to 2 squared times 3 squared times 7 to the first. Now, I need to rule out all of the things that are smaller or equal to 5. Right? I need to rule out those particular factors. But it's a lot easier just to go first and say, how many factors are there? And then just subtract out the very few that are less than or equal to 5. And this is state math counts, so I won't go and explain this one very slowly. But the way you do this is you just go and say, the factors are all 2 to the something, which is 0, 1, or 2. Oh, 3 choices for that. 3 raised to something, which is 0, 1, or 2. 3 choices for that also. So, and 7 is either 0 or 1. I don't have another hand. But like 7 is either to the power 0 or 1. So the answer is 3 times 2 times 2. The 2 choices for the 7. 7 to the 0 or 7 to the 1. So what I have here is the number of factors. I saw that somebody typed into the chat. You take each exponent and add 1, but I actually, and times. And that's what I just explained why. It's because every factor is going to be the prime number to 0, 1, 2, or up to the actual factor it is. Okay, 3 times 3 times 2, that's 9 times 2 is 18. But we need to rule out the ones that are bad. Which ones are bad? Bad. Bad. So I need to know which ones happen to have a factor which is less than or equal to 5. Well, if I look at this, they would be like made with 1, 2, 3, and 4, I think. Those are the only ones. 1, 2, 3, and 4. Because less than or equal to 5, I can get a 1, I can get a 2, I can get a 3, I can get a 4. There's no 5 here. So 4 are bad, and so we subtract the bad ones. 18 minus 4, that should be 14. Okay, so let's see if this works. Let's see. It does. And it was a sneaky trick question. Question 20. In Pierre's sports league, each team plays at most 1 game per day. Furthermore, no team is allowed to play games on 3 consecutive days, nor may any team play 4 or more games in any 5 consecutive days. Under these constraints, what is the maximum number of games Pierre's team could play in a 108-day interval? Good gracious. All right, let's try to understand what in the world's going on here. 1 game per day at most, I get that. No 3 consecutive. Okay, that's fine. No, you can't play. Oh, you can't. You cannot play 4 or more in 5 consecutive days. Okay, first I'm going to be trying to be greedy. All right. 108 day. This is tricky. Okay. If you cannot play games on 3 consecutive days, I'm just going to think of it as like a yeses and nos, okay? So it's like, these are like consecutive days. Start by playing, and play again. But I can't play on 3 consecutive days, so I hit a no. And then I say, oh, okay, I can't go and play 4 or more in any 5 consecutive days. So if I'm trying to be greedy, I could say that this is how I make sure I don't have 4 or more in 5 consecutive days. But now let's be greedy again. And let's go and try to say yes again. Okay, if I say yes again, then the next thing that happens is yes again. Well, let's see. In 5 consecutive days, this is a window of 5 consecutive days now. That seems okay. And then I would say, I'm always going to try to say, let's play if I can, as long as I don't have 3 in a row. And also looking at the 5 consecutive days, I don't have 4. That seems okay. But now we already got this before. When there were 2 yeses, we tried to play again, but that would be 3 yeses in a row. So let's put a no. And if you can see, it's repeating. So then I have this thing. I'm always checking that in any 5 consecutive days, I don't have 4 games. So I can put another yes, just like before. But I would have liked to put a yes, except that would have given me 4 in a row. 4 in the 5 days. So I put a no. And it looks like one way I could do this is just to go and put this pattern over and over and over again. All right. So one possible way to make this happen is I could make this pattern, make this pattern, make this pattern, do it all the way out to the 105th day. Where what I've gotten here is I've gotten here, oops, let's use this. So what I've gotten is in the green, I've gotten 3 out of 5. In the yellow, I've gotten 3 out of 5. And so I can do this all the way out to the 105th day. All right. And if I do this out to the 105th day, I could do this, and this is also the best I can do because I can't take 4 out of the 5. I'm trying to say there's no way I would be able to say that out of the first 5 games I had 4. So like the best I could do anyway is to take 3. I'm only a little bit worried about the edge. The edge is the 108-day interval, okay? So at some point you finish your last batch, 3 out of 5, and then now you have 3 more games, okay? And these 3 more games, if I just continued on with the pattern, I would say yes, yes, no. That's how I'd finish the pattern with this, just saying like continue. And I know that it will be legit because I happen to be in a situation where it was legit under every way of looking at 5 consecutive days. Oh, I like it. You can't play games on 3 consecutive days anyway. So the fact that I only got 2 out of 3 on that's the best I could ever hope for. You couldn't get 3 out of 3. You can see I'm actually proving to us that you cannot do any better than this total. Because here are 5 days, you can't get any more than 3. Here are 5 days, you can't get any more than 3. All the way to the last 5 days, can't get any more than 3. And then you got 3 more days left over, can't get any more than 2 because that's what it says. So in that case, this is really the most. And we also know that it's actually legitimately possible because every overlapping window of 5 days only has at most 3, and we never have 3 yeses in a row. So now let's add this up. So 108 days, this is 105 here. 105 is 21 of these things. So I have here 3 times 21 because I have 21 times 5 is 105. And this thing is going to give me 2 more yeses. 3 times 21 is 63. Plus 2 is 65. So let's see if this works. Let's find out. Yes, it does. And of course, that was also a proof, right? The way that this proof worked is we went and explained you can't do any better on each of these 5-day windows. So, well, that's the most you could ever do, and we were able to do it. Okay, let's keep going. We got 10 more minutes for today, and we're getting them, and they're getting harder. Wow! What is this? That's a lot of 3s you got here. And this looks like it's going to be painful. Painful. Oh, wait. Is that nice? Let's find out. Okay? I have a feeling that it's 3 times a Fibonacci number. But let's go and see what happens. I might be wrong. I might be wrong. Okay. Now, this is like also like the more kind of mathy things you do, the more patterns you find. I'm going to do something really dumb looking. I want to do 3 plus 3 over 3, and I'm not going to call this 1. I'm actually going to say this is... No, that is really dumb. Okay, that is really dumb. Is it? How dumb is it? Okay, let me tell you what I was thinking about. I'm actually already thinking of a recursive method, because this is just too many things. It's gonna be a nuts. See, what I'm trying to say is, like, if I had 3 plus 3, is that what I want? 3 plus 3 divided by, yeah, that's what I wanted, divided by like an a over b. I want to know what this is. If I had 3 plus 3 divided by a over b, that would be 3 plus 3b over a, which is 3a plus 3b divided by a. Yeah, that's okay. Watch what's going to happen here. So what I'm saying is that, why is this relevant, by the way? Because if I look at this whole thing, I can start to say, let's call this thing a sub something. Sub what? Let's see how many 3 pluses are in front. 1, 2, 3, 4, 5. I'm going to call that a sub 5 equals this. Where what I've just done is I've said that's based on how many of these big 3 pluses do I see in front. Okay? That's a sub 5. Now, why did I say that? Because what would a sub 4 be? Well, a sub 5 happens to then be equal to 3 plus 3 divided by a sub 4. Do you agree with this? It's like 3 plus 3 divided by, look at this thing. It looks just like the same, so I'll call that a sub 4. It's going to be easier for me to deal with this way. I know that I've said these a's, and these are different a's, but I'm thinking of them as fractions. So it's like if I had this, this kind of a, is this actually easier? Trying to think if this is actually easier. Not really. Okay, so I'm going to say this is one way you can do this, but actually you probably are just as fast just computing the whole thing out. But I'll say it this way because this is kind of neat also, right? And the important thing is actually at the very end, we do know what a sub 1 is. Let's just call a sub 1, that's just this one of these things. That's just 3 plus 3 over 3, and that's just 4. Okay, so I happen to know that a sub 1 is just 4. And that's because if I had only one of these things, that would just be simply 3 plus 3 over 3. And you can see a sub 2 is the one with 2 of these. That's equal to 3 plus 3 over a sub 1. And so then I just need to figure out what is a5 if I go from 4 and repeat through this process going up. I'm already seeing that you probably can just like do it straight. That probably is just as fast. But anyway, over here I'm just showing how you go from an a sub something to the next a sub something. Because 4 I'm going to call 4 over 1. I'm sort of looking at what happens to numerators and denominators. So if this was 4 over 1, looking at what happened, whenever I do this thing is like, got a number. 3 plus 3 over that number gives me the next one. So that's why I did 3 plus 3 over that thing and see what I get. What I get is 3 plus 3b over a, which is 3a plus 3b over a. So what I just found out is when I go from a over b, I get 3a plus 3b over a. So if I was going to do this, I now know that if I go from a n and get the next one, a n plus 1, what ends up happening is any fraction of the form a over b transforms to 3a plus 3b. I'll call it 3 times a plus b all over a. Like that's all that's happening. So now let's just do it 4 times, okay? So my point is, if I have a sub 1, which is just 4 over 1, I just need to do 4 times of this operation, where I take the fraction, replace it with 3 times the sum of the numerator and the denominator divided by the old numerator. So let's do it 4 times. I get 4 over 1, and that becomes 3 times the sum of 4 and 1. That's 3 times 5, which is 15. I'll just write it as 15. Divided by the old denominator, that's 4. I have to do this 4 times because I need to go from a1 to a5, and that's doing it 4 times. 1 goes to 2, and then 3, and then 4, and then 5. So then I go, the top is going to be 3 times the sum of the 15 and the 4. That's 3 times 19, divided by the old. This is crazy. Okay, I guess. So 3 times 19, that's going to be 57. Oh, wait. I get to divide. I get to cancel. Good. My numbers won't be crazy. I will cancel out 3 and the 5. Divide by 3. So that means that the bottom becomes just 5, 19 over 5. Well, so far I've done it twice. I need to go and do it 4 times. So it will be 3 times 19 plus 5, right? That's 24 divided by 19. That's equal to 72 over 19. And I just need to do it one more time, and then I'll be done. And I guess it wasn't that bad. So one more time, it's going to be 72 over 19. That becomes 3 times the sum. 19 is close to 20. That would give you 92. But subtract 1 is 91. Divided by 72. Yes, we'll finish this now. Because let's start dividing out stuff. 3 into 72, that gives you, what is it, 24? Oh, we just saw that before. 91 is going to be, it's not a prime, but it's a multiple of, it's like 7 times 13, but the 24 doesn't have that. So I just get 91 over 24. Okay, so I think the answer is 91 over 24. And I will be honest, my fancy stuff here probably wasn't helping. Although, well, then you never know. Maybe it helps to have less mistakes. Famous last words as I go and check the answer and see if there's a mistake. 91 over 24. It is! No mistake! Okay, let me go back. Let me explain why I did this. It's because if I look at this, I have a very hard time keeping count. And I'm very afraid of what if I do it the wrong number of times? Or what if I forget to flip a fraction? So the way I did it is I just said, you're really just doing the same thing over and over again. Where your the same thing is 3 plus 3 over whatever you had before. And I look at it and I'm very careful to say the a sub what, like the which term in the sequence, that's just how many big 3's in front there are. And so it's easy for me to say, 4 over 1 is the beginning. 3 plus 1 is 4, 4 over 1. And then after that, just like do the same thing over and over. We got 3 more minutes. Let's play with question number 22. They're getting hard. The equation x squared plus y squared minus 2x plus 4y equals negative 4 is true for how many ordered pairs of integers x comma y? You guys learned this stuff in middle school now? This is insane. Okay, so I need to know how many ordered pairs of integers. Oh. So let's go and start putting the x's together and the y's together. All right, I see something. So if I put the x's together, x squared minus 2x, and the y's together, plus y squared plus 4y, it equals negative 4. Let's use a different color. Okay, that's true, but it looks awfully tantalizing. I wish I could have nice completed squares. This looks like x minus 1 whole thing squared, and it would if I just added a 1. You can't do that unless you add a 1 on the other side. Now, how do I complete the square for this one? Y squared plus 4y, I would like a plus 4 because that makes a perfect square. But if I do that, I better add a 4 on the other side. Okay, and now I have this. It's actually not quite a Diophantine equation because I don't have too much number theory going on here. It's going to be much easier because what is this? This is a perfect square. X minus 1 whole thing squared plus y plus 2 whole thing squared equals 1. Let's use white. Equals 1. Well, how could I do that? If I have integers, not positive, just any integers. If I have integers x and y, I need to add up 2 squared integers and get 1. How do you do that? Only if it's like 0 plus 1. But remember that the way that you can get plus 1 is with negative 1 squared also. So what I'm seeing here is you have a few possibilities. One possibility is that this whole thing is 0. Let's use pink this time. One possibility is this whole thing is 0, and this whole thing is negative 1. Another one is this is 0, and this is plus 1. Another one is that this is minus 1, and this is 0. And the other one is this is plus 1, and this is 0. Those are the 4 ways that I could make 2 integer perfect squares add up to exactly 1. Those are the only ways. And if you can see each of these rows, in order to have x minus 1 equals 0, x is 1. In order for y plus 2 to be negative 1, y is negative 3. Yes. And so I'm saying that each of these rows gives me a different ordered pair, x comma y. And so the answer is actually 4. Because each of these possibilities gives me a different choice of x's and y's. How do I know it's a different choice? It's because it's like if I had certain value fixed for the x minus 1 and fixed for the y plus 2, how you get the x and the y, you just shift these values by the same thing. You always go to get the x, you just plus 1 on each of these. And to get the y, you just minus 2 from each of those. And that's it. So it's 4. Let's see, is this right? It is. And that brings us to have finished question 22. We have spent an entire hour. In the math counts, you actually only have 40 minutes. How you guys managed to finish this whole thing in 40 minutes, well, you're pretty impressive. But what we're trying to do with this live stream is we're just trying to show how you think about them. We're not just trying to do a contest. We're trying to do some interesting math. If you like this, we'll be back tomorrow at the same time, 5 o'clock p.m. Eastern Time. We'll start from question 23, and we'll try to get as far as we can. But thank you for joining, and I'll see you then. Bye-bye.